to be talking about a modified Tricolour imaging process that I've been developing. It's all done, all this photography is done with this instrument. It's a modest instrument. It's a 5-inch, in the abstract they changed it to 125 millimeters. Sorry, I'm still thinking inches. It's a 5-inch refractor by Astrophysics. It's manually guided, the system, as you can see the guide scope on top. This picture was actually taken in Australia. You might see some of the eucalyptus trees in the background. And of all the pictures I'm going to show you in this talk, the astronomical pictures, I think the one that's the most stunning is not an astronomical one, but one of the local inhabitants, this lovely baby koala that my wife photographed while we were in Australia. The camera I'm using with this telescope is this homemade device. It's just a Tupperware and aluminum contraption that looks like this when it's opened up. This is the backing plate for the camera. You'll notice on the left here a 35 millimeter chip of film, and on the right is, this thing's popping out of focus. On the right is the film I use. I cut my film into chips. You'll see in a minute why I need to do that. But this gives you an idea of the size of my negatives as compared with a standard 35 millimeter negative. I'm using medium format film. The reason my film is cut into chips is because I need to shape my backing plate. This gives you an indication of the depression in the center of the backing plate. It's close to a 70 millimeter diameter illuminated circle, and because I don't have an adequate field flattener, I need to shape the plate. This is a very crude mechanism that I use, just concentric layers of Scotch tape that are cut to the right shape. This is what the film looks like when it's loaded. Of course, this is loaded in the dark, and then the plate is turned in the other direction, and the exposure is done. My exposures range from 1 hour to 3.5 hours typically, because my system is just an F6 system. It's a fairly slow system. Now, what I'm doing is trying to produce color photographs with this black and white film. The film that I showed in the previous slide is without doubt the highest resolution and finest grain film available to an astrophotographer, at least an amateur astrophotographer. That's Kodak Technical Pan film, but it is a black and white film. If you want to produce color images, then what you do, and this is a very old process, an old idea. The idea is just photograph your object on this black and white film using different filters. So these are my 72 millimeter diameter filters. Now, if you are familiar at all with the traditional Tricolour process, you know that what people do is they use a red filter, a green filter, and a blue filter. And then you have your RGB exposures that you combine and produce your image. One problem with my optics, I recently acquired new optics, which I hope will help me address this problem. One problem is that even though it is an astrophysics approximatic refractor, it doesn't photograph very far into the blue without getting really bloated stars. So I'm using different shades of yellow filters, as you see here, and a red filter. But the point is I'm capturing color information by using different filters. It's a modification of the basic RGB Tricolour process. So what I do is I load my film chips in the camera and do my exposures. I always mount my negatives in these large glass slide mounts. Sorry about this. Focus. So here you have Eta Carina Nebula, which we did in Australia. On the right is an exposure taken through a red filter. On the left is an exposure taken through a yellow filter. There are very subtle differences, but you should be able to see the greater density and the exposure on the right, which means that this object is brighter in red light than it is in yellow light, which means it's a red nebula. We all know that the Ada Nebula is red. So this is Tricolour. It's photographing the same object through different filters and combining them. Now, after this is done, what I do is I make prints of these negatives and scan them using this 36-bit flatbed scanner that I've owned for 2 or 3 years now. And they come up into my computer. The current incarnation of my computer is a Pentium Pro system with a ridiculous amount of memory. Where's my pointer? Is this in here? You may not be able to read that, but that really is the amount of memory I have in my system, 256 megabytes. The reason I need this amount of memory is because I'm using medium format film, and to capture all the detail that's present in one of my negatives, I really have no choice but to create humongous scans. My scans are usually on the order of 50 or 60 megabytes. By the time I produce the color image, I'm pushing 100 megabytes. And you need this amount of memory to handle that. This is my wife's comment on that. So that's really what my computer looks like. Of course, once you start doing any sort of imaging and using your computer for imaging, you never have enough memory. So this 256 will likely increase. And trying to get it to increase over time, I've got some problems. So the procedure, we take our 2 or 3 negatives. I should say that this will not all be Tricolour. Some of this will be dicolor if you were. And the point is to record color differences by with different exposures. So here's some very old exposures that I took. The North American Pelican nebulas. On the left through a very dark red filter. On the right through a standard yellow filter. The procedure then is to register these images, to rotate and stretch the images as needed to get the stars lined up, and then put them together. An electronic image on your computer just consists of RGB, red, green, blue values put together to form a color image. So this is actually, as I said, a couple of years old. This is the sort of result you get. Now, it's a lot of work, obviously, to do this. Why do this? Why not just use color film? Well, this illustrates the answer to this answers that question, and the answer is if you look at the image on the right, which is taken using a definitively grainy color film, Konica 3200, and the image on the left, you'll see the difference, and the reason why using the black and white technical plan film is advantageous. But you will notice that possibly, if I get a good focus, that the stars on the left are not perfectly registered. Perhaps those in the front can see, maybe in the top right corner, you get a blue star and then a red star. Well, that's because I've had to manually register these images. So if you do this again with some other exposures, oops, this is upside down, but don't worry about it. You'll see the differences in the positions of the stars between the different exposures that led to this misregistration. So this is the process. The pluses of this process are that you get vastly increased resolution as compared with color film because of the characteristics of the black and white film. The spectral response I won't discuss much. The main point here is that the black and white film records wavelengths that color film misses. The minuses are obviously you've got to do a lot more exposures, a lot more effort is involved. And the minus that the last slide illustrates is the registration. How do you get your images registered to produce your final color image? How do you get the stars lined up? Well, this second problem is the one that I want to concentrate on in the few minutes I have remaining. I've been really grappling with this problem over the last couple of years, and a friend of mine who's an ace programmer got interested in this problem. He wrote some code for me, about 9,000 lines of code, C code, which you'll see some sample lines of here. What it does, this code, is it's a multi-program package. The first thing it does is it goes through the image. So these are black and white images that I'm starting with. And remember, the problem is registering them. And so it goes through and it finds the stars. I won't describe any details here, but it does a pretty good job. As you can see, I blacked out the stars here that it's found of finding the stars. And once it's found all the stars, you can see here how many stars it typically finds in one of my medium format exposures. About 80,000 stars. That's pretty average. It computes very precisely the centroid of each of these stars. Then there are some other programs that are used after the centroids are computed. It will do a matching between the centroids. So you've got two images that you kind of match, register. So after computing the centroids of each of these images, it will stretch the images by doing a matching algorithm, which again I won't describe. These are the various programs, components in the package. And it does it. So you start out with your red exposure. This is IC2948, a stellar sky object. A green exposure, well, not really green, it's sort of yellow. These are all red, yellow, and lighter yellow. And red, green, blue. But think of them as red, green, blue. And it will register all the stars. It does a perfect job. In my 5,000 pixel wide images, it'll register the stars to within a quarter of a pixel. And it'll produce this color image after doing this. Okay. I quite get the whole thing in focus anyway. So just for fun, I've taken my original image and applied the wiping out the stars that this program will let you do. So you can just eradicate all the stars. It hasn't quite gotten rid of all the stars. There's some parameters you can set. So it doesn't recognize the brightest regions as stars. You can see some more detail here on how good a job it does of recognizing stars. In particular, one problem we really had to grapple with was how do you pick out stars from nebulosity? And so there's some method we've developed to do this. So here's a black and white image of the lagoon region. And here's the same image without the stars. So that's the original. I'm sure there are other applications of this program to, besides just registering images for Tricolour imaging. And here is just the stars. So I don't know. They're all sort of interesting. It's interesting to compare them. But the point of this, remember, is to produce the final color image. So this is the final Tricolour image, which is the July picture of the 1997 RAC calendar. You'll notice on the left here, you're actually getting some blue. I don't have a blue exposure. How am I getting blue? Well, my point is that the differences in density between, very subtle differences in density between the different exposures, because I'm using very high contrast, high resolution film, let me record blue without a blue exposure, as you can see here. The stretching is really quite a significant problem in exposures like this, because I'm using elastic film as opposed to people like David Mallon who use rigid glass-mounted emulsion for their Tricolour process. I'm using elastic film. I'm never going to get perfect registration by simply rotating and doing a rigid transformation to get one image to match the other. It will never work. So this program, the key component of it is that it'll stretch. It'll use the star centroid data to automatically stretch this part of the image more than that part. And it just does it automatically. I don't need to do any work now with the existence of this code. So just to finish up, I'll just show you a few of the recent results of this process. This is a dicolored image of the North American Nebula. This is the Rosetta Nebula. Here's a bit of a close-up of the Rosetta Nebula. Again, a 5-inch refractor. This is the December picture in this year's calendar, IC 2177. Again, notice that in spite of the fact that I'm not using blue exposure, I'm getting some blue out of this. I hope to get better color information with my new optics, which I unfortunately didn't get a chance to try out before this DA. This is not a tricolor image. This is a piggyback shot taken by my wife Anu when we were in Australia of the large magellanic cloud and the small magellanic cloud. This is what the large magellanic cloud looks like tricolor. So zoom in here. This is the Pulsar and Eta Carina, and this is just to close off my final image, the Eta Carina nebula with my tricolor. Thank you.
Very much, Randy. Tremendous results, incredible images. We have time for a couple of questions. Randy.
Rajiv, are the exposures the same for the different filters?
No, you have to compensate for the exposures. The red filter is usually, the red exposure is usually about twice the yellow exposure. With the new optics, which will let me photograph a greater bandpass, I hope to cut down my exposure time. I'll be able to do an unfiltered exposure, which instead of my minimum hour might be 45 minutes.
Right.
This, Raji, this brings memories back to my high school days, which was a few years ago. Dr. Edwin Land of the Polaroid Corporation wrote a series of articles in 1959 in the Scientific American talking about the Tricolour process, and he described how you can do it. And what I did is have my mother make a 3x3 quilt of a multitude of colors and so on, and then taking two black and white photographs of this quilt, one using an orange filter, another one using a red filter. And of course, filters have a pretty broad acceptance, and so on. But using red and orange filters, and so taking the black and white photographs, and then mounting them in sides, projecting onto the screen, and then putting the same filters in front of the projectors and so on, and you've got all the colors of the rainbow. It was incredible. Just so much.
One more question. At the very back.
Rajiv, since a lot of astronomical objects in the spectral lines, aren't you going to get an accurate colors in many cases?
Well, I mentioned that briefly in passing, and that is an advantage of using black and white film as opposed to color film.
So you're not using RGB filters, so you're not representing the normal color bands.
Well, that doesn't matter. I mean, as long as you've got a filter that reports O3 and H beta.
Yes, as long as you get the coverage.
Yeah, so I chose my yellow filters very deliberately with that in mind. So I have one of my yellow filters that cuts off at 500 nanometers, and another one that goes down to 470. And the difference between those two filters is precisely where the O3 and H beta lines are.
Okay. Thank you very much, Rajiv, for showing us something.